A new class or type of probability situation involves random variables. These are variables that must be quantitative and their outcomes must follow a probability distribution that does not change. A simple example is the outcome rolled on a single die. Here's the probability distribution. A capital letter is used for a random variable, and in this case, x is the outcome on the die. It has 6 values, 1 through 6. When we want to find the probability that x is a 5, we say probability of x equals 5 equals 1/6. The probability that x is greater than 2 equals 4/6, or 2/3. Probability that x equals 2 and x equals 5 implies rolling a die twice and getting a 2 first and then a 5. These are independent events, so the probabilities do not change. In order to have a probability distribution, the following must be true. All possible values of the random variable x must be accounted for. The sum of the probabilities of each variable value must add up to exactly 1, and no probability can be less than 0, and no probability can exceed 1. In all cases, probabilities must be from 0 through 1. 0 is absolutely no chance of happening, and 1 is absolute certainty of an event happening. Returning to our rolling a die once, we see that indeed it is a probability distribution because all 6 outcomes are accounted for, the 6 probabilities add up to 1, and there are no crazy probabilities less than 0 or greater than 1. In contrast, this 6-sided die would not represent a probability distribution, even though all values are accounted for and the sum of probabilities equals 1. It makes no sense to have a negative probability. A random variable can be more complex. Suppose a game is played where someone rolls a die and is awarded points based upon the number rolled. Here are the points. 0 points for rolling a number less than 4, 5 points for rolling a 4, 10 points for a 5, and 25 points for rolling a 6. We would now declare a random variable representing the points scored and not the number rolled. Let's use y. Here would be the probability distribution of y, the points earned. The probabilities are based upon the number rolled on the die, but the numbers of interest are the points earned in the game. Earning 0 points is the sum of probabilities of rolling a 1, 2, or 3 on the die. Examining the probability distribution for y, we see that every outcome of points is accounted for and all probabilities add up to 1. Finally, the examples we just discussed are discrete random variables. There are a finite number of outcomes, but there are continuous random variables as well. The most famous type are normal distributions. Heights of adult women are normally distributed with a mean of 65 inches and a standard deviation of 2.5 inches. We cannot list all of the infinite possible heights in a table. Instead, we show the probability distribution of the random variable values, the women's heights, as a normal distribution. All heights are accounted for along the x-axis, and all of the probabilities, the total area under the curve, equal 1.